Hi guys, so this is the video for us to discuss tutorial 6 which will cover on chapter 8 and 9. So I hope before I start this you already did some of your part, you attempt the questions, alright? So let us go straight. We have two chapters. So first of all, let me just go with chapter 8 first. So this is a summary for chapter 8. Okay, first of all, you need to know about equilibrium constant. One thing that is very important, you must know how to write the expression correctly. How do you write the formula for K correctly? If it is Kp, you must use partial pressure. If Kc, you need to use you need to use um concentration. All right. Okay, so next, this is something that you need to understand. So this equilibrium constant, okay, it can be applied in three parts. Okay, so first is that you need to know about the conversion. How do you convert between Kp and Kc? Okay, so this is what we are going to discuss first. Let's go. All right, so if you look at the first question in tutorial 6, it says that, okay, the equilibrium constant, Kp, has a value of 6.5 exponent negative 4 at 308 Kelvin for the reaction nitrogen monoxide with chlorine. So basically, this is the reactions. All right, so now the question says calculate the value of Kc. Okay, so this one, right, do you need to derive? Maybe if you want to know how to derive you can, okay, but you do not really need to know in detail how to derive because the formula is given. Okay, so what is the given formula given is Kp equal to Kc times RT power delta n. All right, so now when you see this question already give you the Kp. So by right, the R you should know is 0.08206. It is a constant and temperature is given. And you are lucky that this question give you in Kelvin. Okay, so one thing that you need to find is the delta N, which is the change in number of mole between product minus reactant. And then this is what you want to find, which is the Kc. Okay, so let us just try to do this one. First of all, let us find what is delta N. So delta N, okay, is equal to the number of mole of product. So you have 2 mole. So 2 minus, okay, minus reactant. So reactant you have 2 plus 1, right? So 1 mole of Cl2, 2 mole of NO. So total is 3. So delta N here is negative 1. All right? Okay, so now if you rearrange the formula, you will get Kc equal to Kp, all right, over RT delta N, which is in this case, delta N is negative 1. So we can say Kp times RT. Correct? So now you just need to plug in all the values here. Okay, so what is the value for Kp? Kp is 6.5 exponent negative 4 times R is 0.08206 times temperature. Okay, temperature given here is 308 Kelvin. Okay, so and then you press your calculator. The answer should be 0.0164. Okay, so that is how you solve this question. All right. So the same concept we are going to use in the second question. I hope you understand for the first question. Now, let us move to the second question. So, for the second question, it says here the reaction of nitrogen with oxygen to form blah 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 is shown in the equation. So, where is the equation? This is the equation. Okay, at 2000 degrees Celsius. Okay, remember this one given is in 2000 degrees Celsius. Okay, not in Kelvin. Right, the equilibrium constant given here is Kc. So, question wants to know what is the value of Kp. So let us just write the formula again. So we have Kp equal to Kc times RT power of delta N. All right, so if you look at the delta N here, so what is the value of delta N? So delta N here is product minus reactant. Remember that? Okay, final minus initial. So product is 2, 2 mole because 2 NO minus, okay, because your reactant you have 1 mole of nitrogen, 1 mole of oxygen, so total is 2 mole as well. So your delta N is going to be 0. So when something is powered to 0, because you want to find your Kp, correct? So Kp equal to Kc times RT power 0. Remember, anything that is powered to 0 is equal to 1. So in this case, your Kp, okay, because this one equal to 1, so Kp is just equal to Kc. Do you have to do any calculation? Basically, you don't. Okay, so the answer is still 4.1 exponent negative 4. All right, okay. So if you have any questions regarding on how you want to convert between Kp to Kc, remember the formula. If in exams or in tests, okay, we have given you the formula. So all you need to do is just plug it in correctly. Okay? All right, cool. For the next part, I'm going to discuss on problem solving. If you look at these questions, question 3, question number 4, okay, this is on problem solving. So when it comes to problem solving, of course, you need to do calculations, okay? So first of all, you can have 3 different cases when it comes to problem solving. Number 1 is that you have case 1. How do you want to calculate the K given that, let's say, the equilibrium pressure or equilibrium concentration is given, or maybe you need to find it, okay? Second case is that question asks you to calculate the equilibrium pressure or equilibrium concentration of whatever reactants or product or both. Okay, so they give you the K. So in this case, you must make the I stable. And the last case is that you have to do prediction. Sometimes the question can ask you predict this, predict that, okay, or maybe like they are just like asking your opinion, but remember that one is problem solving. So when it comes to prediction of equilibrium shift, you must always calculate the Q value. All right. So let us have a look on the question. So we have question number 3 here. It says the equilibrium constant Kp for the reaction blah 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 blah, okay, is 0.63. So we can extract that Kp equal to 0.63. All right, a rigid cylinder at that temperature contains 1.2 atm of carbon dioxide. Okay, so your CO2 here, you have 1.2 atm. All right, sorry, carbon monoxide. All right, so 1.2 carbon monoxide. Okay, and then you have 0.2 atm of water vapor. So this one is 0.2. Okay, and then you have 0.3 atm of carbon dioxide. So this is 0.3 and 0.27 of hydrogen. So next, the question said predict if the system at equilibrium. So whether that the value of 1.2, 0.2, 0.3, 0.27 are they at equilibrium or not, this is our job. Okay, we need to know if the system is at equilibrium or not. If it is not at equilibrium, what will happen? Okay, so when they say predict here, you straight know that this is coming for case number 3. And when it comes to case number 3, all right, you must calculate the Q value. All right, so let us have a look here. So we need to calculate the Q value. So what is the formula for Q? Formula for Q is going to be exact similar to the K. So Q equal to, all right, so because we are calculating, we have Kp, so we want to calculate the Qp, because if we want to compare, we have to compare the one that is similar. Okay, so apple to apple. So let us just see. So the formula should be pressure of the product over pressure of reactants. So pressure of product CO2 times pressure of hydrogen, okay, divide by the pressure of carbon monoxide times pressure of water. So this one, do we need to power to anything? Okay, we don't have to because all the stoichiometric ratio are 1. Okay, so it's just power 1. Okay, so here, all right, is this all value you know? Yes, right? So you just need to plug in into the formula. So let's see, CO2 here is 0.3. So just put 0.3 times, okay? And then hydrogen is 0.27 divided by the product, which is carbon monoxide 1.2 atm times water is 0.2 atm. So, and then when you calculate this, okay, so let's say 0.3 times 0.27 and then divide by 1.2 and 0.2. So you calculate and then you get Q to be 0.3375. Okay, so what is your job next before you predict is that you need to see how do you compare between QP and KP. So QP is 0.3375, KP is 0.63. So is it bigger than or less than? So basically QP is less than KP, right? Okay, so when QP is less than KP, so we know that system, okay, is the system at equilibrium? Is not at equilibrium. Okay, all right. So how do you want to make sure it reach equilibrium? Okay, by right, if this question, this one would be sufficient. Okay, but how do you, let me just ask you, how do you want to make it at equilibrium? So basically, if you want to make it at equilibrium, you have to increase the Q, correct? If you want to increase the Q, basically, you need to increase more of the product. So how do you want to make sure it produce more product? Okay, so it should actually go to the left or go to the right. Okay, so because your product obviously is at the right of the equation, so you can say system will shift, okay, to the right, or you can just put your own words here, okay, to produce, all right, more reactants or product just now? Product. Okay, so that's it. So the answer is that predict if the system at equilibrium or not. The answer is that system is not at not at equilibrium. The reason is because QP is not equal to KP. All right. Okay, that's it. So the next question is number 4. So for question number 4 here, okay, so let us just figure out which case is this. So the question said the equilibrium constant. Okay, so in this case, they give you the value of Kc, all right, is 49. Okay, so Kc here is 49. Okay, and it says that if 0.7 mole of PCl3 is added to 0.7 mole of Cl2 in a 1 liter reaction vessel at 230 degrees Celsius, calculate the concentration of PCl3 when equilibrium has been established. Okay, so meaning to say this one, the question wants the equilibrium concentration of PCl3. So which case is this? All right. So this is obviously case number 2, in which the question is asking for equilibrium concentration. So let us see how do we want to solve this. Okay. So remember, when it comes to case number 2, you must make I stable. So let us do I stable. All right. So first of all, you need to have this one. Okay. And then like that. Okay. And then like that. Okay. So, and then you have PCl3. Okay. Plus plus Cl2 gas. Okay. And then forms PCl5. Okay. So here you go. All right. So you just make it proper, make it nice. Okay. So this one is going to be ICE, initial change and equilibrium concentration, because this one we are talking about Kc. So, all right, let me just put this as like any unknown. A, B, C, D, E, F, G, H, I. So first of all, what does the question wants? So the question wants to know what is the value here, right? The concentration of PCl3 at equilibrium. So it should be the value of G here. So this is the question mark that we have, all right? Okay, so now, okay, what does the question give? 0.7 mole of PCl3, okay, in a 1 liter. So this one is actually initial concentration. Okay, so here you need to put at A. All right, so you need to put it here. Okay, so all right, so how much do we have? 0.7 mole of PCl3. But remember, we always need in concentration. So just divide 1 liter. Okay, mole per liter is concentration. So basically it's 0.7 molarity. Okay, meanwhile, Cl2 is 0.7 as well. Okay, and what could be the concentration of PCl5 initially? All right, so it should be 0. Right? Before you start the reaction, there are no PCl5. Okay, because this one is I-stable, basically we will not know what is the exact value of the changes. We do not know the value of D, E, and F. But we can assume this to any unknown. For example, okay, let's say I just put here as X. Okay, so let's say PCl3 is reduced by X. So by right, it should be minus X. Cl2 also should be minus X, because X mole or X molarity is used up. So when you use X mole or molarity of PCl3, you will produce X mole of PCl5, right? Get it? So now, do you think you can find the value of here, okay, at equilibrium? So it should be 0.7 minus x, 0.7 minus x, and this one should be x. All right. So when we have these at equilibrium, so basically we can calculate, we can equate this to the Kc. All right. So what's the formula for Kc? So Kc is equal to, okay, concentration of PCl5, all right, divide by concentration of PCl3 times concentration of Cl2. So you will get it to be x over 0.7 minus x square, right? Okay, so now I think you can do the maths, all right? So you do the maths and what is going to be the answer. Okay, so let's just see. The answer should be you have two values of x, okay, which is 0.83 molarity or 0.59 molarity. So by right, you need to reject the value of 0.83. Why? Because if not, at equilibrium, the concentration is going to be less than zero, and that's not making sense, correct? So now you already got your x value. So what do you want just now? You want this value of 0.7 minus x. So you just put 0.7 minus 0.59. So it is 0.11 molarity. All right. Okay, cool. The last part of the chapter. Okay, so if you look at chapter 8, okay, once you know about the equilibrium constant and you understand what is reversible reactions and so on, so we can use it to predict what happened when we change the concentration, temperature, and pressure. So this part is what we call as the application of the Le Chatelier principle. Okay, so as you can see here, you have concentration, temperature, and pressure. All right, so usually the question can also ask, if you look at the lecture notes, what happened if we increase the concentration of this? What happened if we decrease the temperature of the reaction? What happened if we increase the volume? Basically, you are decreasing the pressure. Okay, so when it comes to the question like this, you need to do explanation. All right, so let me just go to the tutorial questions. So for this one, the tutorial questions is asking slightly different, okay? So it says here, nitrogen dioxide can dissociate into nitric acid and oxygen. So you have you have NO2, okay? It can dissociate into NO and oxygen. Under what reaction conditions, okay, meaning to say in this case, temperature, pressure, and concentration, would you expect to produce the largest amount of oxygen? So they want to produce the largest amount of oxygen. So what should you do here? Okay, all right. So first of all, okay, we answer one by one. Okay, the first part is it is asking under what condition, which is, let's say, under what temperature would you expect to produce a large amount of oxygen? So when you want to talk about temperature, you need to know whether this reaction here is it endothermic or exothermic. Okay, so based on this, before that, let us just have a look here. Oxygen here, all right. Oxygen here, is it reactants or is it products? Okay, so you see this is actually a product. So O2 is a product. All right. So now, okay. So this this equation, as you can see, the delta H value. All right. So here, look at this delta H. Oh, why can't I touch it? Okay. Oh, okay. So it's 114 kilojoule. It's positive value. So delta H, oh, sorry. All right. Where do I go here? Delta H is a positive value. Okay. So when delta H is positive, we know that, okay, this reaction is endothermic. Okay. So when the reaction is endothermic, meaning to say this heat, okay, is a part of reactants or is it part of products? Okay. So when this is endothermic, you can say that reactant is a part, heat is a part of the reactants. Okay. So if you want to produce more product, right? If you want to produce more product, basically you need to increase the heat, right? So why? Okay, let's see. The answer is that we increase the temperature. So why? Because when you increase the temperature, all right, you basically increase the amount of heat. Okay, based on Le Chatelier principle, if you increase the heat, okay, system will tend to, okay, what will system do? System will tend to decrease the heat again, right? Okay, try to decrease the heat. So how can it decrease the heat? So the system can consume the heat. So system will consume the heat. So if the system consume the heat, okay, heat is a part of reactant, so it will produce more product. Get it? Okay, so produce more product, which is your product is your oxygen. Okay, so basically your oxygen is produced more under high temperature. So for this reaction, let's say if you're working in industry, what does your boss say? Oh, do you have to increase or decrease the temperature? You must increase the temperature. All right, this is only considering the Le Chatelier principle. Okay, the next one. All right, so we are done with the temperature. So next, look at this one. What does the question say? Is that next is the pressure. So basically, under what pressure would you expect to produce the largest amount of oxygen? You don't have to give the value, okay? It's just, do you want to use high pressure or low pressure? All right. So you want to use high or low pressure. So here, then with the heat, okay? So let's just have a look at the pressure. All right, so when you want to talk about pressure, okay, you have to look at the number of mole of gas in the reactants and also in the products. So here, number of mole of reactants, how many number of mole of gas? You just look at the gas, all right? So gas in reactant, you have 2 mole, okay? And in product, you have 3 mole, okay? So you have 3 mole. So in this case, all right, basically, all right, let's see. Do you have to increase the pressure or do you decrease the pressure? Okay, based on the formula, PV equal to nRT. All right, so, all right, so if you have more number of mole, okay, the system will tend to have a higher pressure. All right. So if you have more number of mole, the system will tend to have higher pressure. So how do you want to make sure the system will tend to have higher pressure? Basically, you have to decrease the pressure, right? Okay. So look at this one. Okay. So let's say you decrease the pressure. Okay, so when you decrease the pressure, for example, you increase the volume, it doesn't matter as long as you can decrease the pressure. Okay, so when you decrease the pressure, what will system do? Because based on Le Chatelier principle, system will always try to oppose the changes that we are doing. Let's say we try to decrease the pressure, system will tend to increase the pressure. So now, if the system want to increase the pressure, the only way is that it must produce the site, okay, it must produce the species that has more number of mole. So in this case, the product has more number of mole. So system tend, okay, to produce, okay, higher number of mole. So it should be reactants or should be product. So it should be product, okay, so which is product. So in this case, under low pressure, okay, so low pressure, you will get more oxygen. Okay, so now we get under high temperature. Okay, so basically first you need high temperature. Okay, for what about pressure? You need low pressure, right? Okay, so lastly, what about the concentration? Okay, so what about concentration? So if you want to look at the concentration, okay, of course, we just look at the concentration of NO2, okay, or NO, the one that is not the oxygen, okay? So let's say in this case, let's just look at NO2. So NO2 is the reactant. So if you want to produce more product, basically you need to add more NO2. And this goes by logic. If you increase the concentration of NO2, the system, okay, will oppose the changes. Remember that? Okay, they will counter any changes that you are making. So system will tend to decrease the concentration of nitrogen NO2, nitrogen dioxide. Okay, so with that, if the system want to decrease the amount of NO2, what will happen is that it will consume, okay, will consume the NO2, right? So if it consume NO2, meaning to say it is producing more product, produce product. So in which your oxygen is a product, okay? So, or if you ask me, can I answer that we reduce, okay, or we remove, okay? Can you remove nitrogen monoxide? Okay, the answer is yes, okay? Why? Because when we remove NO, what will happen is that system, okay, will tend to increase the number of NO. So if it want to produce more NO, basically the system will shift to the right. Okay, so system, okay, produce more product. So it will produce the oxygen as well. Okay, so you can say you can add NO2, all right, or you can say you can remove NO, right? Okay, so those are the four conditions that you can have to make sure you produce the largest amount of oxygen. All right, so that's it. Okay, so we are done with chapter 8. So let's go with the tutorial on chapter 9, and we just have 4 questions here. Okay, so first of all, when it comes to acid and base, all right, this is the mind map of this chapter. So for the acids and base, first of all, you need to know the definition. Okay, so why do you need to know the definition? So that you can identify in a chemical equations which one is acid, which one is base, which one is conjugate acid, and which one is conjugate base. So from there, okay, you can start to do your calculations and so on. Okay, so when it comes to calculation, the concept that you learn in chapter 8 and 9 are the same, that you have dissociation constant. Okay, so dissociation constant is just like equilibrium constant. Okay, so for water, you have Kw, all right? So meanwhile, for acid, you have Ka, and for base, you have Kb. Okay, makes sense, right? Okay. So now, what about the P scale? So P scale is, for example, you have pH, you have pKa, you have pOH, okay? So all of this is actually P is just the negative log. For example, if you say pH, meaning to say it's negative log of H plus concentration. So if you say pKa, meaning to say it's a negative log of Ka value. Get it? All right, so remember pKw has a constant value of 14. Why? Because Kw is 1 exponent negative 14. So when you negative log it, you will get 14. And then you can also have problem solving questions. So problem solving questions, meaning to say that you still have just like the cases. Okay, you have case number 1, case number 2, case number 3, but it is different a bit from chapter 8. Here, you don't have prediction in case number 3. All right, so we'll go through this one by one. Okay, so let us just have a look at the first question of chapter 9. So it says here, identify the Bronsted-Lowry acid and the Bronsted-Lowry base on the left side, because of course, acid and base will be on the reactant side, conjugate acid and base will be on the product side. Remember that. Okay, so now, if you look at what is the definition of Bronsted-Lowry acid and base, okay, Bronsted-Lowry acid is proton donor, Bronsted-Lowry base is proton acceptor. So how do you want to identify them based on these questions? Okay, so if you look at this one, all right, so just first of all, my tips is that you find the pair. For example, NH4 plus, the pair is NH3. Okay, meanwhile, all right, let me just find another color here. Okay. Meanwhile, Cn minus, the pair is HCN. Okay. So look at NH4 plus. NH4 plus, okay, it goes to NH3. So initially it has 4 proton or 4 hydrogen, and then now become in product, you have 3. So meaning to say it has loose proton, meaning to say it has donates its proton. So based on the Bronsted-Lowry acid base definition, okay, what is meant by Bronsted-Lowry acid is proton donor. Therefore, NH4 plus here is acid. Okay, so this one is acid. So basically, if one is acid, another one should be base. Okay, but if you want to get more confirmation, look at this. Cn minus become HCN from 0 hydrogen to 1 hydrogen. All right, so basically here is going to be the base. All right, so because Cn minus, it accepts 1 proton to become HCN. So base is a proton acceptor. All right, so once you produce that, okay, if we look at the reverse side, okay, NH3 become NH4 plus. We look at the reverse side, okay, because we want to look at the conjugate acid and base. So NH3, if it wants to become NH4 plus, meaning to say it has to accept 1 proton, right? So in this case, it is going to be base, right? But we do not call it base. We call it as conjugate base. So HCN is going to be conjugate acid. So basically, if you can identify for sure one of these species, you can identify all. Okay, let us just have a look at this, the second question. Okay, so let's just look at who is a pair HCOOH to HCOO minus. So HCOOH, initially there are 2 hydrogen. And then, okay, or 2 proton we say. And then when it become in the product side, you have 1 proton. Okay, 1 has lost, meaning to say 1 has been donated. So HCOOH is a proton donor. So remember, proton donor is the Bronsted acid. Okay, so this one is going to be acid. So acid going to produce conjugate base. All right. Meanwhile, so if you know this is acid, obviously this is going to be base. All right. And another one here is conjugate acid. Right. That's why I said you just need to know one only. Okay. All right. Cool. Okay, let us have a look at problem solving questions. So as you can see here, when it comes to problem solving, we will just play around this part. Okay, so you see it goes from pH and then H plus and then Ka and then Kb or pKb, pKa and so on. Okay, so let us have a look at this question. Next question is on 7, question number 7. Formic acid is a weak acid with a pKa of 3.74. In this case, 3.74 is pKa. So basically, you know pKa, you can know the Ka. So here it says draw up a reaction table for the reaction of 0.3 molar. Reaction table is just basically ice table here, okay, for the reaction of 0.3 molar formic acid with water and calculate its pH and percent dissociation. So there are 2 parts that the question wants. One is that the question wants the pH, another one the question wants the percent dissociation. So which case this one is, okay? So basically, the first one, it asks you to calculate the pH from the Ka, and then that is case number 2. And then the question also asks you to calculate the ionization percent. So basically, this is case number 3. You need to use the formula. Okay, remember the formula is not given in the final exam. So let us have a look. All right. So we now have our reaction table, right? And this is a formula for Ka. Right? For Ka is going to be the concentration of H3O plus times concentration of HCOO minus divided by the concentration of HCOOH. Okay? So water is not part of the formula. So you can just ignore water. Why? Water is liquid form. Make sure when you write here, should be here is aqueous, this one is aqueous, this one is aqueous. Oh, sorry. This one is liquid, okay, and this one is aqueous. Okay? So first, you have Ka. Ka is actually the formula here. So we need to plug in all the concentration of H3O plus at equilibrium, HCOO minus at equilibrium, and also HCOOH at equilibrium. So we need to find it. Okay. So first, when it says here the reaction of 0.3 molar formic acid. So 0.3 molar here, is it initial? Is it change, or is it equilibrium concentration of the formic acid? So the answer is it should be initial concentration. Okay, so that 0.3, you will put it here. All right, so what about the concentration of HCOO minus? It should be 0, okay, initially. And H3O plus, okay, you can say 0. Or if you want to be more precise, you can say 10 negative 7. 1 exponent 10 negative 7. Why? The reason is because you have water, and water have auto ionization. So you can start with 10 minus 7. But if you want to say 0, also fine. Okay? All right, for your level. Okay, so next. Okay, and then we want to do this one. So we need to know what is the changes, but we cannot get the numbers. So we can just put this into any unknown. For example, we use X. So when the HCOOH dissociate, okay, meaning to say negative X mole of HCOOH will dissociate into X mole of HCOO minus and X mole of H3O plus. So then from there, you can construct what is the equation for the equilibrium concentration. So HCOOH is going to be 0.3 minus X, and then here is going to be X, and this one is going to be 10 minus 7 plus X. Because 1 exponent negative 7 is very small, you can just make it almost equal to X, all right? So now we got all of these values. Okay, so these values are ready. So can we just plug into the formula? Yes. Okay, we can just plug into the formula down here. All right. Except that, what is the value of Ka? Because we know the pKa is 3.74, we can calculate the Ka. Because, all right, pKa is equal to negative log of Ka. Oh, sorry. All right. So we can know what is the value of Ka. So here, the value of K is going to be shift log, or 10 power of negative 3.74. Okay, and then I just plug in the value of H3O plus and HCO minus. I just take it X and X, so it should be X squared. So from there, you can get also the concentration of HCOOH, 0.3 minus X. So now, all right, we just need to solve the equations. Okay, just get the quadratic equations. Use your calculator again. All right, and then you're going to get your X. Okay, so what's going to be the value of X? Okay, you will get two values of X again. So you need to choose which one to reject, because this one is negative value. So obviously, you're going to reject this. Okay, so now you get the value of X, and this value of X is also equal to the concentration of H plus, okay, or H3O plus. So now that you get the concentration of H3O plus or the H plus, can you calculate the pH? Yes, of course. Okay, you're going to use this formula, pH equal to negative log H plus. So the value is there, 7.298. So you just plug into the value, the pH is going to be 2.137. Okay, that's quite a low pH. All right, so then we are done with the first question. Okay, so we have answered the first question to find the pH of this solution. Second question is that it asks to calculate the percent dissociation. So if you want to know the percent dissociation, remember, okay, you need to know the formula. The formula should be the concentration of H plus at equilibrium divided by the concentration of acid initial. Okay, so you just need to know what is the value here, okay, and what is the value here. You divide it and times 100. For example, this is a concentration of H3O plus or H plus at equilibrium, and this is the initial concentration of the acid. So you times 100 and you will get 2.43%. And that is quite a low ionization percent, but it's fine. Okay, that is the answer. Okay, all right. Is everything cool with you? Okay, so now let's go to the last two questions. Okay, so this is also on problem solving. So for question 8, it says here, okay, so the pH of 0.2 molar solution of weak base pyridine, okay, which is this is the base pyridine, is 8.59. Draw up a reaction table, meaning to say ice table for the reaction of 0.2 molar pyridine with water, and calculate the Kb. So where do we go from here? Okay, so the question is asking you to calculate the Kb here. All right, so let me just take the pink ink. So we want to calculate the Kb. So what do we have? Okay, so we have the pH. So we are going to start with pH. So how do you want to navigate your way to find the Kb? All right. So there are so many ways to navigate, and it depends on how your brain works. Okay, so if for me, okay, this is how my brain works. Okay, so how am I going to solve it? Okay, first of all, we have to know what is the concentration of OH minus at equilibrium, and we can get this from the POH value, right? So remember, pKa, which is equal to 14, is equal to pH plus POH. So POH is basically going to be 14 minus the pH, which is 8.59. So you see here, this is the POH value. All right. Now, what am I trying to find here? OH minus is actually negative log OH minus is equal to POH. So I'm trying to find what is the value of OH minus. So that's why 10 power of negative 14 minus 8.59. Right? So do you get it? Okay, so if you look at this one, so when we calculate, okay, we will get 3.89 exponent negative 6. All right? Okay, so now we have this one. Remember, this one is at equilibrium. Right? So where can you put this? You can put this here, 3.89 exponent negative 6. So what is the initial concentration of OH minus? Is going to be 0 by right. Okay? Or you can, if you want to say, oh, it's 1 exponent negative 7, you can put it as well. Okay, all right, but that is very, very small value. All right, so that's why I didn't put it in. Okay, so from there, we know also the initial concentration of the C5H5 and H is going to be 0 as well. And what about this one? Okay, so this is going to be the changes. Okay, so the changes is 3.89 exponent negative 6, which is positive for the product. So C5H H5 and H are the same. Okay, this is actually ions, so plus. All right, so you get 3.89 exponent negative 6. So once you know this one, you can know what is also the changes for the reactant, okay, which is the pyridine. Okay, and then do you know what is the initial concentration of the pyridine? Yes, because it is given in the questions, okay, which is 0.2 molar solution. So we know it should be 0.2 here. So can you get the E here? Yes, it's going to be 0.2 minus 3.89 exponent negative 7 and negative 6. So why do I write almost equal to 0.2? Because, okay, let me just press a calculator. 0.2 minus 3.89 exponent negative 6. Okay, the answer is going to be 0.1999961, and that is very small. So it is just almost equal to 0.2 again. So that's why I just write 0.2. Even if I want to round off, okay, I'm just going to get 0.200. So that is still 0.2. Okay? So now the question is asking to calculate the Kb. So what is the formula for Kb? Kb is going to be equal to the concentration of the OH minus times the concentration of C5H5 and H plus. All right. And then divide by the concentration of the pyridine itself. Okay. And this all must be at equilibrium. Right. So here, let's just put the values. Why this 3.89 exponent negative 6 square, okay, should be half here. All right, so because you have the concentration of OH minus and C5H5 and H. And then it's going to be divided by 0.2, so the answer is 7.56 exponent negative 11. Do we have to put units? No. All right, because K here does not have any units. Okay, so that is the answer. All right, so what about the last one here? Okay, so the last question. Okay, the English are fond of soggy French fries, blah, 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 drenched in vinegar. And this vinegar is made up of 0.83 molar of acetic acid. So we say that if the acetic acid in vinegar is 0.47% dissociated, calculate the Ka value. Okay, so this one is a bit complex, okay, but can be calculated. Okay, so the question is actually on case number 1. Okay, so we want to calculate the K. All right, So we need to know the equilibrium concentration of H plus, or we can know the pH or pOH. In this case, the question start to give you the percent ionization. So basically, if you have percent ionization, you can get the concentration of the H plus at equilibrium. All right. So how do you do this? So this is the percent ionization. It is actually equal to concentration of H plus at equilibrium divided by the concentration of the acid initial concentration. Is it given? Yes, it's given in the question, which is 0.83, right? Okay, so and then the formula times 100%. And then we do the maths, okay, and then we will get the concentration of H plus to be 3.9 exponent negative 3. So remember, this 3.9 exponent negative 3 is actually the formula, this is the concentration at equilibrium. So just put it here, correct? So from that, if the initial we say 0, or if you want to say 1 exponent negative 7 again, no problem. Okay, so we can get this one. So from here, all right, you can also get the change it in concentration for acetate ion, 3.901 exponent negative 3 as well. So here is the same. All right. So now, what is the initial concentration of the acetic acid? 0.83. And then what about the changes? Minus 3.901 exponent negative 3, because this value is not very small. So we cannot just like almost 0.83. So just make it 0.826. So here, one thing I said many times, you really need to know how to write the equation for the K. So it's going to be the product over reactant. So the product is basically H plus. So Ka is equal to concentration of H plus times concentration of CH3COO minus divided by CH3COOH, right? So it's going to be 3.9 exponent negative 3 square, all right, because they are the same, okay, and divide by 0.826. So then just press your calculator and get the answer. The answer is going to be 1.84 exponent negative 5. So in the case that, let's say the question asks you what is the value for pKa, then you just negative log of the Ka, right? So the question can just play around here. Right, so that's it for tutorial 6, which cover chapters 8 and chapter 9. Right, if you have any question, you can just ask your lecturers or you can ask me as well. Okay, that's all the best. Dah gempak. Gempak siap dah.